Okay, so let's do the second example for strongly connected components. So this is the given directed graph of 8 vertices. So you can start depth first search say from vertex 1. So push vertex 1 to the regular stack. From vertex 1 you can go to vertex 2, so push it to the regular stack. From vertex 2 you can go to 3, push it to the regular stack, and from 3 you can go to vertex 4. So these are the 4 vertices that are pushed. So now from vertex 4 you have say a back edge to 1 and you cannot go anywhere else. So you pop out vertex 4, that's the first vertex to be popped out of the regular stack. So you push that to the SCC stack. So that's vertex 4 in the SCC stack. So the top of the regular stack is vertex 3. You can't go anywhere else to a new vertex. This edge to 1 is a back edge because 1 is still in the stack. So you pop out vertex 3, that's the second vertex to be popped out of the regular stack. So you push it now to the SCC stack. Back to 2 at the top of the regular stack, we cannot go anywhere else. So you pop out vertex 2 and push it to the SCC stack. So now we are left with just 1 at the top in the regular stack, and we cannot go anywhere else from 1. So we pop out vertex 1 as the fourth vertex from the regular stack. So push vertex 1 to the SCC stack. So we started one instance of depth first search on this directed graph from 1 when you're able to visit 2, 3 and 4, but not yet 5, 6, 7, 8. So we had to run another instance of depth first search on the given graph. So you start with vertex 5 and push it to the regular stack. So that is the fifth vertex to be pushed to the regular stack. And then from 5 you can go to 6, that's the sixth vertex to be pushed. And then from 6 you can go to 8, that's the seventh vertex to be pushed. Now from 8 you have a back edge to 5 and you can't go anywhere else from 8, so you pop out 8. So 8 is the fifth vertex to be popped out of a regular stack, so you push it to the SCC stack. So you just pile up all the vertices in the same SCC stack. So we piled up this vertices in the SCC stack, so just continue the same SCC stack, push the other vertices in the other instance of that first search. So vertex 8 is now pushed to the SCC stack. So now we are back to 6 at the top of the regular stack. We cannot go anywhere else, so pop out 6 from the regular stack and push it to the SCC stack. And then from 5 you cannot go anywhere else, so pop out vertex 5 and push to the SCC stack. So in the second instance of depth first search, we're able to just visit 5, 6 and 8. So now we have to start another instance of depth first search from 7. And so these two edges should be called cross edges because they are two vertices that are visited in the earlier instance of depth first search. So from 7 we cannot go anywhere else, so just pop out 7. So that will be now on the top of the SCC stack. So that's the first step of running depth first search of one or more instances on given directed graph and building up this SCC stack. So now we are going to go to the second step, again some sequence of iterations of running depth first search on the reverse graph. So how you build the reverse graph, just change the directions of the edges in the given from the given graph. So 1 to 2, so there's an edge now from 2 to 1. 3 to 1 means edge from 1 to 3, so and so on the reverse graph. So for all this 8 involving all these 8 vertices. So now start running depth first search on the reverse graph. So from which vertex? It depends on which vertex is in the top of the SCC stack. So vertex 7 is in the top of the SCC stack. So start running depth first search from 7. So we'll run depth first search from 7 on this reverse graph, push vertex 7 to the, again some regular stack we are just using for keeping track of push and pop orders. So push it, but you cannot go anywhere else from vertex 7, so you pop out vertex 7 right away. So that means started from 7, the depth first search, and we cannot go anywhere else, so you pop out 7, that stack, the regular stack becomes empty. So that means like 7 is on its own strongly connected component. We are not able to visit any other vertex from 7 in this reverse graph. So what we'll do is remove vertex 7 and all its associated edges. So this is now the new reverse graph. So also remove 7 from the SCC stack. So this is now the SCC stack with vertex 5 at the top. So on this second new reverse graph, run a new iteration of depth first search starting from vertex 5, which is in the top of this SCC stack. So start from vertex 5, push it to some regular stack, the second vertex to be pushed, and then you can go to vertex 8, push it to the regular stack, and then go to vertex 6, push it. Now from vertex 6 you have back edge to 5. Cannot go anywhere else from vertex 6, so it's time to pop out vertex 6 and back to 8. We cannot go anywhere else, so time to pop out 8, and then back to 5. We have to pop out vertex 5 also. So the regular stack becomes empty, so that is a separate instance of depth first search. We started from 5 and we are able to visit 6 and 8. So 5, 6, 8 are said to form one strongly connected component. So basically in each instance of depth first search that you run on this reverse graph, all the vertices that are reachable in that instance are said to form a strongly connected component. So you also to proceed to the third iteration, remove 5, 6, 8 and the associated edges, as well as remove 5, 6, 8 from the SCC stack. So this is what you are going to be left with. The 1, 2, 3, 4 is now the modified reverse graph, and then the SCC stack has just 1, 2, 3, 4 in it. So now start depth first search on this reverse graph from the vertex that is in the top of this SCC stack, which is vertex 1. So we start from vertex 1. Now from vertex 1 we can go to either 3 or 4. We'll visit 3. No, I'm not sure why. Okay, I just visited 4. You could visit 3. So I visited 4. So push vertex 1. From 1 you can go to 4, and from 4 you can go to 3. You could have gone to 3 also. It's okay, doesn't matter. So then from 4 to 3, and then from 3 to 2. So you keep just pushing. Push 1, push 4, push 3, push 2, and from 2 you cannot go anywhere else to a new vertex, so it's time to pop out 2. So pop out 2, then back to 3, cannot go anywhere else, pop out 6, back to 4, cannot go anywhere else, back to 1. So 1, 2, 3, 4. If you went from 1 to 3, things would be like this: 1 to 3, push 3, then push 2, then you can't go anywhere else, so pop out 2, pop out 3, back to 1. Now from 1 you can go to 4, and then back to 1. So we are not interested in classifying edges as tree edges, cross edges, back edges, and so on. So just trying to find out what vertices are reachable or can be visited in this particular instance of depth first search. So 1, 2, 3, 4 are the vertices that can be visited in this current instance of depth first search. So these 4 vertices are said to form one strongly connected component. So you remove all the vertices and the associated edges, and then also remove them from the stack. There are no more vertices remaining. So we are done with this process. So put together what we have so far. So 1, 2, 3, 4 is one set of strongly connected component, and then 5, 6, 8 is another strongly connected component that we identified in the second iteration, and the first iteration identified 7 on its own strongly connected component. So these are the 3 strongly connected components of this given directed graph. And earlier I just showed there are 2 weakly connected components of this directed graph, because when you consider the undirected version, 1, 2, 3, 4 is one set of vertices that are reachable to each other, and 5, 6, 7, 8 is one set that are reachable to each other. So you should be able to find for a given directed graph both its strongly connected components by going through this process, as well as the weakly connected components by showing the undirected version. You don't need to run depth first search on the undirected version, because it's already done some earlier cases. So we just draw the undirected version and show me, okay, these are the weakly connected components. That's good enough. But for strongly connected components, you need to show all the steps like I have shown here. You should not just write the answer by kind of guessing out what vertices are reachable to each other. Okay. Alright, so let me save this video and then I'll come back.